So hi everyone again, and welcome to the first keynote session of the 5G and wireless IoT Buffalo Day. My name is Michael Langberg, and I'm a faculty here in the EE department at UB. And so it's my great pleasure to introduce our first keynote speaker, Dr. Ness Shroff. Dr. Shroff received his PhD degree from Columbia in 1994 and joined Purdue University immediately afterwards. From Purdue, Dr. Shroff joined the ECE and the CSE departments at The Ohio State University, where he holds the Ohio Eminent Scholar Chaired Professorship of Networking and Communications. From 2009 to 2012, he also served as a guest chaired professor of wireless communications at Tsinghua University and as an honorary guest professor at Shanghai Jietong University. He currently holds a visiting position at the IIT Bombay. Dr. Shroff's research focuses on fundamental problems in machine learning, network optimization, stochastic control, and algorithmic design. His work contributes to the design, control, performance, pricing, and security of complex systems, such as communication networks, computing, storage, and cloud-based systems, social networks, and recommendation systems. He currently serves as the principal investigator and institute director of the NSF AI Institute on Future Edge Networks and Distributed Intelligence. Dr. Shroff has served his community in numerous editorships and committees. He served as the editor-in-chief of the IEEE ACM Transactions on Networking and currently serves as the steering committee chair of ACM and Mobihawk. Dr. Shroff is a fellow of the IEEE and an NSF Career Awardee. His papers have received numerous awards at the top venues. These include the Best Paper Award at Infocom 2006, Infocom 2008, Infocom 2016, the Best Paper of the Year in the Journal of Communication and Networking in 2005, and in Computer Networks in 2003. And in 2014, Dr. Shroff received the IEEE Infocom Achievement Award for seminal contributions to scheduling and resource allocation in wireless networks. So it's really with a great delight that I pass the stage on to Dr. Shroff, who's going to speak today on next generation networks and distributed intelligence.
Thank you so much, Michael. Can you hear me? Can everyone hear me fine?
Yes, we can hear you and see you fine. Thank you.
All right, so I'm going to just share my screen. All right.
Excellent.
Okay. That was a very, very kind introduction. So once again, I'm Ness Shroff from the Ohio State University, and I'm the Institute Director of this new NSF AI Institute that's focused on designing future edge networks and distributed intelligence. And the reason I say that is because what I'm going to do is spend a little bit of time talking about the Institute vision and then talking about some of the key research thrusts that the Institute is focused on, primarily because I feel that many of the research problems that we look at in the Institute might be of interest to the broader community. And so this will take approximately 25 to 30 minutes. And then the rest of the time, I will take one case study as an example, which is the case study of a very important problem called edge caching, and show how machine learning techniques can be developed to improve performance in that particular case. All right, so let's begin with the vision of the Institute. So the idea of the Institute is to harness the synergies between networking and artificial intelligence to create not only a research, but also an education, knowledge transfer, and workforce development environment that will hopefully help establish US leadership in future generation edge networks, as well as distributed intelligence. And of course, this is a very broad and challenging problem. And to that end, what we have done is we have organized and assembled a team of outstanding researchers from the 11 universities that you saw on the first page on the map, as well as several companies, various DoD labs like the Army Research Lab, the Air Force Research Lab, US Naval Lab, as well as MITRE. And more recently, we've also gone global. So we've extended our reach, and we are now collaborating with KAIST, Seoul National University, and Korea University in South Korea, as well as the Indian Institute of Technology in Bombay, and then the Indian Institute of Technology in Madras. In Delhi, sorry. All right, so here is the scope of our research setup. So this figure kind of gives you a little bit of an idea of what we are looking at. So firstly, let me define what we mean by the network edge. Okay, so a very precise but probably useless definition of the network edge is everything that's outside of the core of the network. Okay, so what do we really mean by that? This includes all types of wireless networks, be they robotic networks, drone networks, vehicular networks, cellular networks, Wi-Fi, etc. Right? In addition to that, it also includes, the outside part of the wireline network. So things that are connected to not the core data centers, but the edge data centers. It includes, edge clouds. You can have camera networks that could be wired or wireline. All of this are part of the edge. And so the bottom layer in this figure represents the physical network, while the top layer represents the intelligence plane that we plan to design as part of the scope of the institute in order to control these networks. And the research plan is organized across 8 thrusts that span 2 broad symbiotic research areas that I'll talk about a little bit more in depth. The first meta research area is AI for networks, and the other one is networks for AI. Each of these have 4 thrusts in them. And the idea is that the foundational research that we develop will be fleshed out, and its impact will be deepened by exploring important use cases. And to that end, we have identified 3 critical use cases. The first one is on ubiquitous sensing and networking. The second one is the interplay between machines, humans, and mobility. And the third one is about programmable, virtualizable networks. And we've already started to understand how to connect the key research thrusts to specific experimental platforms. If you look at the bottom layer, we've connected different cases to different power platforms. These are NSF-funded platforms, as well as identified which of our partners are interested in helping us implement particular use cases. So, when we talk about an institute of this scale, we need to sort of think of what are some of the key differentiators. But this is not only about the institute, it's also about a philosophy which I think the networking community, I'd be happy to share with and, take criticism or further feedback on it. The first one is that we believe that while AI has been enormously successful at solving a number of engineering problems, the network itself is a very different, dynamical, and complex beast, where simply applying known AI techniques will not be good enough. So we strongly believe and strongly advocate that we need to develop new foundational AI advances that take into account the very specific requirements and dynamics of the networks. The constraints that the networks have, hard constraints. You have, movement that happens in the network, at multi-time scales, millimeter seconds, seconds, minutes, etc. All of these dynamics need to be taken into account. And perhaps most importantly, you don't want to throw away the decades of domain knowledge that we have developed in designing networks, right? And just come up with a black box solution that simply, doesn't work well in the networking scenario, because the networking environment, unlike image processing, etc., is a very, very dynamic environment, and so needs new foundational AI to make it happen. The other focus has been our bet that the future of AI will indeed be distributed, right? So we are already seeing that. We already see that end user applications are run with AI, but oftentimes these applications are standalone. They don't communicate with each other. And now we have sort of an opportunity to design intelligent networks that can interconnect all of these devices to potentially unleash, the power of collaboration to solve very important distributed AI problems. So to that end, one of the goals of the Institute is to develop AI-aware networks and network-aware AI. And finally, to make something really happen, you need to shorten the time scales of interaction between use case and foundational research. And that's sort of what we call, the virtuous cycle from theory to implementation. And so the idea is that we are focused very much on, making sure that the foundational work that we do translates to large-scale experimentation, and then eventually translates to industry and DoD implementation. All right, so let me now spend a few minutes briefly introducing the research thrusts. And what I'll do is that for some of the thrusts, not all, because we don't have the time for that, I will provide a couple of examples that sort of go a little bit, deeper into some of the problems that the thrust actually looks at. So we start at the physical layer, and one of the goals of the first thrusts is, how does one re-engineer the physical fabric for wireless communications in order to expand the capacity set itself? Okay, so how does sort of one leverage the physical knowledge in order to basically provide a larger capacity to play with in terms of our resource allocation and so on. And to that end, we've looked at several different directions. I'm going to give you a couple of research challenges. The first one is motivated by the fact that physics-based models have already been used to solve complex systems. For example, leveraging physical models into a neural network to speed up prediction. And the question becomes, can such models be used to design machine learning tools to better estimate parameters of interest, multipath components, mobility, etc.? And in particular, what we've already shown is that physics-based models can be integrated with machine learning tools to make better decisions for problems such as beam searching, beam forming, and substantially accelerate the convergence times of the selection process. Another very interesting and sort of open direction is the one of discovering efficient codes through machine learning. So here the idea is the following. If you look at coding theory over the last several decades, you will see that the progress has been modest over the years, with occasional breakthroughs that happen, like turbo codes, etc., which are really based on human ingenuity, right, and typically focused on linear codes. And so one of the questions that I think is a very important and open question is, can machine learning be used to expedite discovery and perhaps neural networks be used to expand the search space to nonlinear codes. And here there are several key challenges. Number of code words is extremely large. You have issues of generalizing from one SNR and block length to sort of other SNRs and larger block lengths. And so to overcome these challenges, it's very critical that domain knowledge from communication, coding, and information theories be used in order to solve the problem. And there have been very promising preliminary works from our group, Sewong O, etc., in designing low latency nonlinear codes. But of course, there are plenty more problems here related to this very broad area of developing efficient codes and communications that remain open. Okay, so the second thrust is about AI-based network resource allocation. And here our focus is on developing new AI techniques for the design and control of next generation networks, taking into account, as we said initially, practical network constraints, taking into account network dynamics such as non-stationarity. And here the focus is, can AI algorithms be developed in multi-time scale? Can we handle complexities that might be different for different heterogeneous devices? What about the information data complexity in terms of essentially the samples that we receive? So the first big research challenge is, can we design low complexity and sample efficient AI algorithms? So the idea here is we need new strategies to rapidly learn and adapt to unknown and time-varying conditions. So big question here is, how can machine learning tools be developed for efficient and scalable network resource allocation and control that have low sample complexity, that have low communication complexity, have low computing complexity, and can take into account the very important network environment that we are dealing with, like I said, non-stationary dynamics, hard and soft constraints, and potentially multiple objectives. So this is where the traditional optimization tools may not be enough, and this is where AI-centric approaches may yield significant results. And already preliminary work shows that this is indeed possible. Another big challenge is, how does one deal with incomplete network state information, which is going to happen in dynamic systems all the time, right? So for example, many network control functions cannot wait for all the data to arrive before they need to make decisions. So here we advocate the use of multi-scale machine learning tools. As a sort of example, one could use local data for real-time control, but maybe more historical data to determine the policy itself, right? And then once you do this, can you show something nice about your policy? Can these techniques be shown to say, okay, this policy has near optimal performance? Can they be made scalable, etc.? The third thrust is also about resource allocation and control, but it goes from single agent to multi-agent. And here the idea is that basically, if you develop solutions that are optimized for single agent AI, when these agents interact with each other, you may actually get a solution that is far less desirable than one thought of. A simple example could be just setting handoff thresholds. If you basically, focus on a single cell and develop an AI mechanism to optimize what the handoff threshold would be, for a single cell, when you have multiple base stations interacting with each other, it may turn out that threshold is so low that it may overwhelm the neighboring base stations. And therefore, it's very important to develop multi-agent AI techniques and the problem becomes even more exacerbated when you go from a fully cooperative to a potentially non-cooperative scenario. Another thrust, which is very important for designing networks, is the one on network security. And here our focus is on developing new AI tools and techniques to ensure that the network is secure, intrusion-free, and highly robust. The aim here is that we would like to develop AI tools and techniques in the design of the network itself and not as an afterthought. And there are many interesting problems that one can deal with. AI can be used to automate things like anomaly detection, attacks, analysis of network protocol specifications, protocol implementations, etc. So this is a very broad area of research, very exciting area of research that, in my opinion, has to be performed if you want to design XG networks, because security is going to become an increasingly important aspect of designing these systems. Now, shifting gears, we now go from the AI for networks domain to the network for AI domain. And that brings us to thrust 5, where the goal is to develop distributed AI tools that will seamlessly adapt by their operation by taking into account the network constraints. So these could be computation constraints, communication constraints, data constraints. And here again, let me give you a couple of examples. The first one is if you wanted to solve a network-aware distributed optimization or network-aware machine learning solution. So if you look at the way traditional distributed machine learning works, is that it assumes reliable communication, typically between a central aggregating server and worker nodes. But if you look at, edge networks, workers are communication constrained devices. These are mobile phones, IoT sensors, etc. And they have very different needs. They have heterogeneous computing needs. They have heterogeneous communication channels, sometimes unreliable. And a big question is, what are some fundamental trade-offs between communication efficiency, computational capability, and machine learning performance? And there's this very exciting preliminary work done by one of our colleagues, Joshi, and all from Carnegie Mellon, where she shows that for stochastic gradient descent, which is the heart of many machine learning problems, communication gains can be substantial when you transmit infrequently when these algorithms are far away from convergence, and you transmit frequently when the algorithms are much closer to convergence. And this allows you to, improve the performance of the system, quite a bit. A big question is, can we further improve performance by overlapping communication, local computation, compression, coding, etc. Another example is one of solving large-scale machine learning problems. So, it's well known that many of these problems are highly parallelizable. Then they can be distributed over many servers, but they also suffer from a very important setback, which is that you have to deal with what are known as stragglers. These are the slowest tasks because you might have links that are very, delayed or low speed. You might have servers that are overloaded. You might have servers that are rebooting. And roughly, and if you look at big data centers, roughly servers are rebooting 10% of the time. And these substantially impact the overall quality of the performance. And some very practical solutions that Google and others have proposed, for example, by monitoring the progress and replicating slower tasks, have shown to have significant limitations in performance. And this is where an emerging area that sort of came out about 6-7 years ago is called coded computation. It's a very promising area and basically allows the final results to be recovered from a subset of completed tasks. So you resolve the straggler problem. But the problem with this area is that the focus has been from an information theoretic, coding theoretic aspect. And what they've done is that they've resolved the straggler problem, but by injecting the code, each parallel job now becomes more complex. So in a sense, one problem gets transferred to another problem. And in fact, we've shown in large-scale simulations that if you do coded computation the way it's traditionally done in the literature, you can actually increase the overall time rather than decrease it. And so a big question here is, can coded computation take into account the structure of the machine learning problem, for example, things like sparsity, and be adaptive to the heterogeneous edge? And indeed, that's feasible. We've sort of already designed codes which are efficient and sparse and can resolve both the straggler problem without increasing the time of solving each individual parallel job. Thrust 6 goes beyond having the distributed AI meeting the constraints of the network, and actually advocates that we can re-engineer the networks themselves, adaptively through slicing, etc. Okay, in order to meet the needs of the distributed AI. And here there are many questions. You have to deal with network operations for managing AI side uncertainty, managing network side uncertainty, etc. Then thrust 7 is about the interaction between human AI and the networks. So, while we all would like to see AI-based solutions completely remove, the human from the system, the reality is that at least over the next decade or two, it's very unlikely that a human will not be involved in many decisions that complex networks face. And so a better approach is, how can we develop new collaborative methods across this human AI networks interface to make the overall system more efficient than it would be by either the human or the machine themselves. And that's an open question which deals with things like explainability of these systems, providing the right interfaces. So there's a lot of theory as well as practice that go into the design of these systems. And the final thrust, and by no means the least important, is one of providing privacy. So the question here becomes, how do you design and control these networks such that they're privacy aware and can be optimized to facilitate protection from information leakage and attacks, right? So especially becomes important when you don't have a trusted curator to make the decisions for you. And this is where there's a lot of very exciting work being done in differential privacy, which has been focused a lot on federated learning, but actually can be extended to other distributed learning areas, online learning, reinforcement learning, etc. All right. So I hope that it's clear that there are many exciting problems out there where machine learning can be used to substantially improve the performance of complex systems. But I wanted to give you a little bit of a cautionary tale here. And this actually comes from World War II, which sort of will clearly, I hope, explain why context matters so much with data. So it turns out that in World War II, the Royal Air Force lost a lot of planes to German anti-aircraft fire, and then decided to armor them. And some of the engineers said, hey, let's look at the data to figure out where to armor these planes. And the obvious solution was, they looked at planes that returned from missions and counted up all of the bullet holes and said, okay, if this area has had the most bullet holes, we need to put extra armors there. Now, this is the obvious solution, but it was wrong. Can someone tell me, unmute yourself and tell me why it was wrong?
I think I actually know the answer, but the point was that they should have looked at the planes that did not come back to the base.
Yes, indeed. Yes, it was sort of obvious but wrong, because if a plane made it back safely, even though it had a lot of bullet holes, it meant that the bullet holes that the planes that came back safely were not in areas that were dangerous. So in fact, what you want to do is you want to armor up areas that do not have bullet holes. For example, the engine, because planes with holes in the engine never in fact came back, right? So the bottom line is it's very important to use and interpret the data carefully, and this is where domain knowledge becomes very, very useful. So if you are looking at a medical application, you better understand the medical application well enough, in order to make progress with AI, etc. All right. Now let me spend the next few minutes studying, talking about one particular case study, which is that of edge caching, and I'll explain how machine learning tools can be designed to solve the edge caching problem. So edge caching is critical for a number of edge applications and use cases. In autonomous transportation, you might want to store, geographic congestion, environmental accidents, etc., information at edges for fast decision making. Personalized education, you want to store educational materials based on users' interests. Edge computing, you might want to store some pre-computed data at the edges, for example, product embeddings for recommendation services in order to speed up the computation. So edge caching is quite an important area. And also it's very different from the core. So for example, you might have much more individual demands at the edges because the edge devices typically serve a small group of users. And so it's very, very unlikely that if a user asks for music A, they're going to ask for music A again very, very soon. So strategies such as least recently used, are not optimized for such dynamics and may introduce significant inefficiency. So your machine learning can be quite helpful to predict individual demand dynamics and adaptively update the cache contents. And this is some work that we've done in the past. But my focus is going to be on another problem where the edge caching performance is actually impacted by other storage layers from the edge to the core in a complex and implicit manner. And how do you address this implicit impact of multiple storage layer through machine learning and update the edge caching decisions is going to be the focus of this talk. And one of the reasons why this is going to be the focus of the talk is because this implicit relationships between different functions in a network happens in many more scenarios than even just edge caching. And machine learning is an interesting tool that allows us to sort of reveal this relationship in a sense and be able to design better systems. So let's start by quickly overviewing content delivery networks for those who might not know. These content delivery networks typically have multiple caching layers. The edge caches are closest to the users. They have the smallest capacity, obviously, but also the smallest delay. Then you have intermediate caches that have, quite a bit larger capacity than the edge, but also quite a bit of a larger delay. And then, of course, you have backend storage, which have the largest capacity. And we're going to assume here that it can store the entire data set. But these could have very, very large delays. So you generally don't want to get something from the backend data storage unless you absolutely need to. So typically you have hundreds of edge caches in a large, content delivery network connected to an intermediate cache and tens of intermediate caches connected to a backend data storage. So here is an animation that shows you, what could happen if a request were to arrive from a user for a particular item. So if that item is stored in the edge cache, it's served directly. If it's not in the edge cache, then it goes to the intermediate cache, and if it's there, it's served from there. Otherwise, if there's a cache miss there as well, it's finally retrieved from the backend storage. Now, why is the problem of edge caching challenging? Because it turns out that the delay of fetching the miss data, which is really the miss cost, depends on where the data is stored, whether it's stored in the intermediate cache or whether it's stored in the backend cache. But whether a data item is stored in the intermediate cache is not really known to the edge cache, and it cannot predict it because the content of the intermediate caches are impacted not only by one edge cache, but hundreds of edge caches. So the miss cost of a data item really is unknown to the edge cache. And so a big question becomes, how does one strategically estimate the miss costs and use these to design efficient edge caching policies, which is very different from what happens at the core. So let's say our system goal is to minimize the expected accumulated miss costs. And if you knew the miss cost of an individual item, which is you knew where they were a priori, then the optimal policy becomes very simple. You cache the items that have the largest popularity distribution times the miss cost. But in reality, of course, as I mentioned, you don't know the miss cost. And so there have been several works in the systems literature, for example, this well-known paper on hyperbolic caching in Usenix, which basically do the following. They estimate the miss cost by taking the average of previous observations of the missed items and then cache the items that have the largest product of the popularity distribution times the estimated miss cost. But there is a big issue with this heuristic solution. It ignores what would happen in the future. So it ignores the impact of the caching decisions on estimating the average costs in the future because of two reasons. One is that a sample of missed costs can be observed only when the requested data is a miss. And the other reason is that you were making your decisions, greedily. So in the learning parlance, you're only exploiting, but not exploring. So let me sort of explain this a little bit more clearly. So let's say you have only two data items. So let's just look at a very toy example, D1 and D2. And let's assume that they have equal probability. And let's say that the edge cache has capacity just 1. And the miss cost of this item is 2. If the item is served from the intermediate cache, it's 10 if the item is served from the backend storage. But since the content of the intermediate cache changes over time, let's say you have these two sample paths. So for item D1, for the first 2 time slots is actually available in the intermediate cache. And then for the rest of the time slots, it's not available in the intermediate cache. So you have to get it from the backend cache. For item D2, for the first 2 items, first 2 time slots, it's not available in the intermediate cache, and then it gets stored in the intermediate cache. And now, what will the heuristic strategy be? Based on the first 2 observations, it will cache item D2 because estimated miss cost is lower. But the heuristic solution will never replace item D2 by D1, which is what you want to do in the future, because D2 is already cached and its future miss costs will not be observed. And if you look at the average miss cost of D1, no matter how long the time scale, the time is, it's always going to be less than 10. So this sort of just gives you an idea that you can make pretty poor decisions if you don't design the solution, by taking into account what could happen potentially in the future. So what does online learning tell us? Basically, it says that you need an exploration versus exploitation trade-off. And so our solution will be, develop caching schemes that are guided by these online principles that appropriately balance the trade-off between, exploration and exploitation. And this turns out to be closely related to an area called stochastic combinatorial multi-arm bandits. But there are new challenges beyond conventional multi-arm bandits that I'll talk about a little bit later. All right, so now let's get to the model. So we have a set of M data items, D1 through DM, with unit sizes. And let's say that the cache size is K, where of course K is typically much less than M. This is the edge cache size. We'll assume a discrete time model. And at each time slot, T, there is a data request R of T that has a particular popularity distribution, let's say P sub I. And let's assume that PI is known for the time being. This can all be relaxed. And the cost to serve the item depends on where the item is fetched from. So let's just say for simplicity that the cost is 0 if the item is served from the edge cache. Doesn't have to be, we can have it some small value here as well. Cost is CI if the item is served from the intermediate cache, and the cost is CB if the item is served from the backend cache. The only thing we need is CB greater than CI greater than CE if you have an edge cache cost which is greater than 0. Okay. And the caching decisions of intermediate cache, as I said before, is not known at the edge cache. So at time t, let qi be the probability that item di is not stored in the intermediate cache. And gamma I is the expected miss cost for item di, which is sort of given by this equation right here. And the only thing we will assume is that gamma I is a function of qi, and without loss of generality, you can also order the data items such as the product of gamma I times pi is decreasing with respect to I. You'll see why I've done the ordering in this way. It just makes it easier to analyze. But doesn't change the generalizability of the solution at all. So let's say our overall goal is to minimize the expected accumulated miss cost for edge caching, which can, for a particular policy over a time horizon n, be given as the expected sum of getting the item from the intermediate cache times the cost of getting the item from the intermediate cache plus the expected cost of getting it from the backend cache. Now, of course, if you had an edge cache, you'd also have another equation if the cost of the edge cache was not 0. All right. So if you knew these QIs, okay, if you knew the cache miss probability at the intermediate caches, then the solution is straightforward. You always cache the first K item, since the product of the popularity distribution times gamma I is decreasing. But in fact, you don't know these QIs. And so what we would like to do is we would like to develop a learning-based solution that adaptively learns these QIs and then updates the cache content. So basically, the idea is that at time t, after serving request t, we can decide A, whether to load that request onto the edge cache if it's not already cached, and then which data item to evict if the edge cache is full. So this is what we do. And here is sort of the connection between the edge caching and the stochastic combinatorial multi-arm bandits. So as you can see, there are lots of similarities, but there is a very important difference which changes the analysis in a significant way, which is that in the edge caching case, you have an additional constraint on the action set, because the caching decision in the edge caching case at time t depend on the request that arrives and the caching decisions that happen at time t-1, while the action set of a stochastic combinatorial multi-arm bandit can be arbitrarily selected. Okay, so you cannot directly apply the analysis to edge cache. All right, so here is these equations that roughly kind of show you our policy. What we want to do is we want to compute an estimate of this QI of t, and so we basically set the estimates initially to be 0, and at time t we first calculate the sample mean of QI, and then we estimate this QI of t by using a Kullback-Leibler, lower confidence bound based solution. So basically what we do is we underestimate QI by a lower confidence bound, and the underestimation is done because we want to encourage exploitation. We want to encourage exploration as time t increases. And then we update the content of the cache by taking the miss cost as a function of this estimated QI. So let's say if item di arrives at time t, if that item is stored in the edge cache, of course we don't need to update anything. If it's not stored in the edge cache, we load it into the edge cache if the product of its popularity times the estimated miss cost is greater than the product of the popularity times the estimated miss cost of any item currently in the cache. And then we basically kick out the item that has the smallest product if the edge cache were full. All right, so how do we analyze the performance? We analyze the performance using a very well-known and well-understood metric called regret. Basically, the regret is the cost of your particular policy, so pi, minus the cost of the optimal policy, let's say with known quantities. So for example, in this case, it would be with the known QIs. So you already know how to calculate this, right? And this regret, it turns out, can be written in terms of the expectation of two values, ti in, which is the duration of time when di is stored in the edge cache, and ti out, which is the duration of time when di is not stored in the edge cache. And we're able to get an upper bound on our policy. So what we can show is that a proposed Kullback-Leibler lower confidence bound based edge caching policy has logarithmic regret. And if you look closely, you will see that this upper bound matches exactly with this lower bound. So basically the lower bound says that for any caching policy, okay, we will have a regret that is no less than exactly this bound, which is the same as the upper bound here. So basically what this tells us is that the policy that we have designed for edge caching policy is asymptotically optimal, not only in terms of the regret term, but also in terms of the constants. And actually it turns out to be much better than the heuristic solution. In the interest of time, I'll sort of skip the proof and give you some numerical results. The first one is, when all of the items have the same popularity distribution, you can see that the heuristic that's in the systems literature performs much poorer than the learning-based policy. This one shows that, even for popularity distributions that are like ZIF distributions, which model a lot of Facebook images and so on quite well, the same result holds true. This is basically shows us that even if you had unknown popularity distributions, you can still use our policy and estimate the sample mean in the KL-LCB policy, and you still get much better performance. And finally, this result is just showing you that the policy is asymptotically optimal as predicted by the theoretical analysis. All right, so what are some of the takeaways here? The first takeaway is that you want to underestimate this QI, this miss probability, because you want to encourage exploration even when t is large, right? So you basically want to make sure that you're always, searching and probing. You might do it less frequently as you get closer to the optimal solution, but you're still doing it in order to avoid the issue of the heuristic solution. And how to do it appropriately, how to optimize the rate of exploration is given by our Kullback-Leber-based lower confidence bound policy. And the solution is immediately generalizable, and we've already done it in multiple directions. Unknown popularity distribution is easy to do. You don't need identical data sizes. You can solve that problem as well. Bottom line is machine learning techniques can be developed to substantially improve the edge caching performance as long as you take the constraints and the dynamics of the system into account, as I had repeatedly said before. There are many interesting future directions for the edge caching problem. One of them is, how does one jointly optimize edge and intermediate caches with limited and delayed information exchange? How do you, for example, deal with the situation where you might have time-varying popularity distributions, which means you have non-stationarity, and some of the work we've done in the past on non-stationarity can be used there. Anyway, I'll leave this to you, and I think I'm probably running out of time, so I will sort of stop right here. Thank you.
Good. Thank you very much for that excellent presentation. I think the details of the thrusts were so exciting, and the problems that were presented were really fundamental, and also the last part on the second half on the caching was beautiful. This tightness and the regret.